Hey everybody, it's Cullen from Trustbridge, and what we're kicking off here is a little bit of a webinar series. So in each of these, we're hoping to cover off an important design consideration as it relates to making better products and focusing in particular on what Trustbridge Design is zeroed in on, which is design for manufacturability. We think this is really the thing that is most lost in the market of designers right now. You can make really cool products, and increasingly every day with the advancements we've seen in 3D printing and advanced manufacturing technologies, including CNC, some advanced sheet metal forming, some really cool technologies we see across our manufacturing network. There are some tremendous new abilities to come up with geometries that were previously impossible. At the same time, that isn't to say everything is possible, and that is where, when the rubber meets the road, just because you can make it doesn't mean you should make it. Doesn't mean that you necessarily are taking full advantage of the right technology for the end use application when you try and take things out of the design phase, prototyping phase, and get it into bridge production or certainly mass production. And the more that you can kind of streamline that transition, where your prototype part pretty closely resembles your bridge part, which pretty closely resembles your final mass manufactured part, the better off you're going to be in terms of getting products to market in a timely fashion and in a cost-effective fashion. So the very first topic that we want to cover today is how to design parts that don't blow your manufacturing budget. Now, we've got a whole bunch of other topics coming up in the series, but today's is particularly oriented around the choices you can make so that cost effectiveness is achieved. So in today's session, we are going to aim to drive towards a clearer understanding of key cost drivers when you are designing a product, and then secondly, how you design to reduce waste of underlying material, and then also waste of labor. So if we cover all of those out successfully, then I think we will be in a spot where we've got a clearer understanding of how to make cost-effective design choices to support your end manufactured product. So without further ado, let's talk about our first focal point, which is understanding key cost drivers. So the first of those key cost drivers that we want to call out is material costs and sourcing dynamics. Okay, this shouldn't be a surprise to anybody, but different materials cost different amounts. And interestingly enough, the cost of that underlying material is not uniform as you might think it is across processes. When you think about CNC machining for a part, stainless steel is a great choice. In contrast, a material like Inconel is a really expensive choice because it's not nearly as easily cut. That is not necessarily the case when we get into the space of 3D printing. In the world of 3D printing, stainless steel powder costs effectively the same as Inconel powder because that particular product, Inconel, and there are a few different grades of Inconel that are key focal materials for 3D printing. The atomization process that results in fine powder grains, it gets applied across Inconel, and it's done at similar volumes to when it's done at stainless steel. So you actually don't get a meaningful cost savings, nor is it meaningfully easier for the machine to process. If we're talking about stainless steel versus Inconel. So that's a really important thing to kind of understand. The material choice there, its ready availability, the pricing volatility that might come with that particular material if you're trying to dynamically source it, and then also minimum order quantities. All of those are key inputs here to what can drive up a material's cost. And so that's a really important one to think about as a key cost driver of your project. Second key focal point is around geometric complexity and impact on cycle time. So this kind of harkens back to one of the comments I made at the outset here, which is really you can make some spectacular geometries now that you couldn't make in the past, right? Powder bed 3D printing, for example, allows for interlocking structures, allows for really complex kind of scaffold-like lattice structures on the interior of a part, which can allow you to eliminate tremendous amounts of weight and actually achieve outcomes that were previously impossible even with the most sophisticated casting. I think in particular about captured bodies, right? But the reality of this is that we can also drive unnecessary complexity and extra cost with that, because while 3D printing, the cost of complexity is relatively free, 3D printing is an expensive process, particularly when we're talking about metal at scale. Improvements have been made there, but oftentimes a less complex geometry allows for easier finishing, easier inspection, easier post-processing, all of which can drive out some of the cost. And this isn't just 3D printing, obviously. It handles complexity really, really well. But when we talk about things like CNC machining, where, hey, if your part design requires a whole bunch of complexity, programming costs can go up, the ability of a regular 3-axis machine to handle the part may go down, which requires a bunch of different fixturing and setups and all these things where maybe you want to level up to a 4 or 5 or 6 or 7-axis machine for which the machine time is more expensive, right? And that extends into things like tight radii, thin walls. Those are things that thin radii require multiple tool changes to get down to those really fine details. Thin walls require machines to slow down, or in certain circumstances require for kind of other accommodations to be made to support those thin walls. So all these things can drive up costs. So that's the second key cost driver that we want to highlight. The third is setup, tooling, and fixturing implications. And I kind of alluded to this just moments ago, but if you are designing a part and you have it in mind for 3-axis CNC machining, for instance, the number of setups that that's going to require can go up substantially if you don't design with that end application in mind. Excuse me. So if you think about it, you're going to fixture a part. Usually you've got a nice base on the platen from which you are cutting. If you've got a tool that's going to just machine straight down and then move in an XY plane and then come down to a certain point and cut, that works great. That's very simple. If you need to instead change that and flip it on its side or angles or anything like that, that requires multiple setups. It requires human intervention. The machine isn't just doing its own thing anymore, but rather there's a substantial ongoing involvement of people. And that is not simply in moving it around, but then obviously designing the particular fixtures that are going to allow for that machining to be completed. So multiple setups, custom fixtures, all those things drive up cost, on top of the fact that they also impact repeatability, because you're introducing new elements here. That refixturing process, there can be human error involved in that, in addition to the time, which may impact your repeatability. So that is another key area. That can impact your cost drivers. A final area that we want to tee up when we're talking about understanding your cost drivers is tolerances and their effect on scrap and quality assurance. Okay, so general rule of thumb, only make your tolerances as tight as they need to be to accomplish the task at hand. Let your functional requirements drive your tolerances, not the other way around. Now, it's true that most CNC machinists, for instance, achieve a 5 thou tolerance regardless. But that is not actually true for every single shop. That's a CNC machine. There are lots of applications for which you've got kind of older school machining technologies where, you know, pretty much any machine cutting it will do. And if that is an option, then you can bypass some of the CNC machining and utilize maybe older technology, but sufficiently effective technology to achieve your end outcome. By that same token, if you've got half a thou tolerance, a half thou inch tolerance or a 1,000th of an inch tolerance for a given space that really does not need it, then you're going to be slowing down the process, because what ends up happening is multiple tool changes are required to try and hit that tolerances. There may be post-processing that's required. So during your quality assurance process at the end, our post-processing step becomes much more complex with a whole lot of post-processing to bring what is it by default, maybe a 5 thou tolerance down to that 1 thou, and that can require a bunch of different post-processing techniques to achieve it, on top of the inspection and measurement that allows you to achieve that end outcome. So don't think for a second just because your CAD design can achieve it, and also don't think because even the machine that you're putting it on can necessarily achieve it, means that's where you should default the tolerance level to. Make sure that that is the truly desired intent, because your manufacturer is going to be looking at those critical tolerances and baking that into their post-process plan. And if they don't need to be, because it's non-critical for you, that obviously eliminates some of that expense that is tied up in human labor or machine setups. So those are the 4 key areas we want to highlight here when we're talking about understanding key cost drivers. Now we're going to go ahead and gear shift into what you do with it from there. And that is talking about how to design to reduce waste and labor expense. Okay, so there are 3 key areas in which we see the opportunity to design your part or product to reduce waste and labor. The first of those is designing for assembly and reduced part count. Okay, so as we think about all of our parts and products, right? How many parts does it take to achieve the end goal? What's interesting about this, and this is like a really complex calculation, so it's not always easily achieved, but there are ways to do it. And the main one involves actually looking up your bill of material to see what sort of things can be bought off the shelf versus what needs to be custom manufactured. Okay, it's very possible that there are items off the shelf that could work their way into your design. It's important to remember, though, that those off-the-shelf parts are not only the cost of that off-the-shelf production, which should be low, right? Because these are parts that are mass-produced at scale. That's how they end up on a shelf. The second piece that needs to be considered here is the assembly time. So those simpler parts, mass-manufactured parts, they still need to go in to the end product and the final assembly. And so when you are accounting for that lower cost for the off-the-shelf part, do be mindful of the fact that it needs to be assembled. What might or might not be more cost-effective is to combine parts together, for instance. Go ahead and bake in elements of that off-the-shelf part so that you machine or you cast or you 3D print or you mold or you generate a sheet metal product that combines multiple parts into a single part, and then that in turn allows for assembly time to be accelerated. In certain circumstances, inspection may be positively impacted by this as well. Not always, but sometimes. You'd also be mindful of the fact that fasteners, the connection points tend to be the failure points, right? Between 2 parts, that's where we tend to have issues. So the fasteners that are going to exist between assembling 2 parts or kind of soldering plans, whatever it is that you have in mind to weld these 2 parts together, that's something that can, again, drive up your cost. If you want to reduce waste, reduce labor, that assembly step, that post-processing can be eliminated if you design multiple parts into one with assembly in mind. Second key area that we wanted to highlight when you're thinking about designing to reduce waste and labor is simplifying shapes for faster machining or molding. Okay, so as we think about this, there are a few key areas where you can think about what you truly need out of a part. And again, sometimes we're making little aesthetic trade-offs here. Sometimes those matter, sometimes they don't. So for instance, when we think about deep cavities, for instance, that's a great place to break a tool at the end of a CNC machine, right? If you're milling and you're going into a deep cavity there, that is a great recipe to create a lot of stress on that tool. You need a longer, thinner tool to access that particular deep cavity, and that is a great opportunity to break a tool, right? So just think about it. Like if you were putting a long skinny pencil and you're trying to do this manually, right? What kind of stress would exist if you've got a really long skinny pencil versus a fat short pencil, right? At the end of the day, that's kind of what milling is doing. So just think in terms of what might snap that pencil and how, long and skinny or short and fat the tool ideally could be to address that space. If you can design with a short, fat pencil in mind, versus a skinny, long pencil, all the better. Second is overhangs, right? So part overhangs, this is something that tends to come up more in 3D printing and CNC machining, but it exists to an extent in machining world and with other technologies as well. When you design with overhangs, and I'll highlight 3D printing here right now. Those overhangs, a lot of the 3D printing processes need to be supported. Okay, so again, this is extensible to an extent for other manufacturing processes, but when you think about, for instance, extrusion 3D printing builds parts a lot like a manufacturing crew at a construction site builds a building, right? That construction crew is standing up a building. What do they do first? They think about the scaffolding that's going to hold up the structure. If you've got elements that jut out from the core structure, there needs to be a really strong base to support that. Otherwise, you can see drooping or a collapse of the machine. Same thing applies in the world of 3D printing. If you're going to have an overhang, you either need to design, and this is really what 3D printing technologies do, they will pre-build that scaffolding to support those overhangs that are jutting out too far. So you really want to keep your overhangs relatively short. If you can design with fillets, some kind of your own scaffold structure to kind of bow out and hold things up, thinking about like you're building like a tree, right? Where you kind of make it a little more gradual in support of the limbs of your tree and all the leaves that sit on top of it. You don't kind of make an immediate straight line out. Think about designing like a tree and minimizing those direct overhangs that are kind of flat 90-degree angles and as a result can create some issues. This extends into casting. 3D printing was the example I gave. CNC machining tends not to have this same effect. So again, you got to be thinking about the process you're designing for, but overhangs are another key area to consider. And then lastly, undercuts, same sort of deal. That's an injection molding term that you tend to hear a lot more, but those sorts of undercuts and in CNC machining world as well. Think about your design. If you've got to reposition and do some cutting from underneath it, like we said in the previous section, you're going to need to refixture it, right? So we're going to have to turn that part upside down so your 3-axis machine can access the undercuts. And again, that's a cost driver, right? So simplify those shapes. Try not to make really deep cavities. Pick simpler, shorter, fatter cavities if you can, to the extent that you need cavities. Since you do overhangs, support them. Be thoughtful about filleting so that your overhangs aren't extreme challenges for the manufacturing process you're chasing. And then similarly, undercuts, avoid them where you can. Flatten that out. Don't require the cut as a secondary op. That will eliminate some cost for you. And then the last area that we wanted to highlight in terms of designing to reduce waste and labor is attempting to minimize the need for secondary operations. Okay, so when we talk about this, and we kind of alluded to it earlier, if you can design without the need for post-process grit blast or polishing or heavy inspection, obviously that's going to eliminate some costs. So, one thing that can be done way back at the beginning, we talked about material choice, right? If your finishing is going to require a post-processing step, maybe you want to anodize your parts to achieve a desired outcome, that can make a lot of sense with aluminum. But then again, if you can use another material that has the key properties you're going after, that's going to eliminate a post-processing step. And those post-processing steps, remember, they don't always reside inside the manufacturer, the most cost-effective and most efficient manufacturer out there. A lot of times that post-processing step exists elsewhere. So if you're designing with the expectation of using that, something that we at Trustbridge, when we get into the Trustbridge manufacturing phase, we're very mindful of, right? Who actually has this in-house? They don't have it in-house. We generally don't match a customer to that particular supplier because we know they're going to have to outsource that step. It's going to drive up time. It's going to drive up costs since they don't actually control the asset themselves. And that complex finishing can drive up expense. Post-processing in general, too, if you just contemplate that as a secondary op, it's a great opportunity to create expense that doesn't necessarily need to be there. One of those things I highlighted is inspection, right? So as part of your post-processing, the part comes off and then ultimately gets inspected before it goes off to you as the end consumer. And naturally, that post-processing can be done at any number of different levels. There's obviously the work that's done to the actual work piece. And then there's the inspection that takes place afterwards. If you've got a ton of those secondary post-processing steps, it requires for inspection to confirm that everything went according to plan. If you could eliminate all that and just take it right off the machine, machines do hold default tolerances. But if you're kind of manipulating the part afterwards, that creates additional work around that inspection step in addition to the actual post-processing that's done to the part. All those things, again, drive up your secondary operations, drives up your costs. So that is it. This is the moment when we go ahead and gear shift into a discussion of particular case studies that speak to this. And for that, I want to go ahead and throw the discussion to my colleague Shivam. Shivam leads our design team. He is out of office today, taking care of something with his father, who is on the mend, we're happy to say, but means he couldn't be here today. So as it relates to case examples, I hope that the examples I've kind of given on the fly here have sufficiently met your need to kind of understand some of the challenges that lay in front of you. Again, as always, if you're looking for design support, we here at Trustbridge Design have a deep breadth of experience across, frankly, thousands of materials, thousands of projects across, I would say, hundreds of different manufacturing technologies or machines specifically, probably several dozen different manufacturing technologies. Maybe we're getting the hundreds by now. But roll it all up, that is what we do here at Trustbridge is the design for manufacturability as a core focal point, because again, we're backed by a network of hundreds of manufacturers globally that we've built a sourcing engine for that really serves their needs in terms of helping customers like you identify the right partner on the planet to be doing the very specific work that you're looking to have done. So I hope you got some great value out of this. If you did, I encourage you to like and subscribe to the Trustbridge channel. And if you have further questions, don't hesitate to reach out or jump on our website to submit a request for design support or a request for manufacturing support. We would be elated to support you however we can. Thanks again for your time and look forward to working.